Good morning, everybody, and thank you very much for the kind introduction. And first, I would like to thank Professor Sonnadara and Dr. Pereira for inviting me here to give this invited lecture. And the topic of my lecture, as you all can see, it's a lightning flash, and I am sure that all of you are familiar with lightning flashes. All of you have seen it, and I am sure some of you may have had a close encounter with lightning flashes. So, I will try to organize my presentation under these 6 categories, starting with mythology, and then I will go to describe physical properties, and then something about energy dissipation, interaction with humans, and then triggered lightning and interaction with the upper atmosphere. First of all, if you take any civilization, they treated lightning as a supernatural event, and every culture had a god who is responsible for lightning. So you have lightning gods in Scandinavia, Greece, India, China, North America, South America, Africa, and any other country that is not mentioned here. And all these civilizations, they treat it as a weapon of God. And for example, we Sri Lankans curse our enemies by saying, "May lightning strike them 7 times." But actually, lightning is not a weapon of God, as you will realize by the end of this lecture. First of all, I would like to show you the beginning of lightning research. It started with Benjamin Franklin, and he suspected that thundercloud, lightning is electrical phenomenon, and he suggested an experiment because he did small experiments with charged bodies, and he knew that if you have a charged body and take a needle close to that, you will get electrical discharges from the needle and it will neutralize the charged body. So based on that knowledge, he suggested this experiment, and he said that erect a very tall conductor about 10 meters from a little hut and place that conductor on an insulating body. And he said that whenever there is a thunderstorm, you can get electrical discharges from the tip of this conductor, and the conductor will be electrically charged. And if you take your hand close to that, you can get a spark. And he suggested this experiment to the Royal Society in London, but they did not believe in this experiment. So they did not perform this experiment, but the French scientist, they managed to do this experiment in 1752, and the whole village was gathered there to see sparks coming out from one of the old soldiers who conducted this experiment. But in the meantime, Franklin was anxious to do his own experiment, so he managed to fly a kite, and then during a thunderstorm, and he managed to accumulate charges, which is coming along this string of the kite, and then those charges, they got accumulated at a key which is hanging from this string, and he managed to get sparks from this string. And in this way, he proved that there is electricity in the thundercloud, and lightning is an electrical phenomenon. So let me tell you a little bit about thundercloud. And if you look at a thundercloud, you see a cloud like this. But if you go into the details, a thundercloud looks like this. The height of the cloud can be about 12 to 15 kilometers, and the width of the thundercloud could be about 10 kilometers. And you have about 10 to the power 8 kilograms of water in a typical thundercloud. We call them cumulonimbus clouds. And the electrical charge, it could be about 100 coulombs, and the electrical potential of the thundercloud is about 100 megavolts. And how do you create electrical charges in the thundercloud? It is actually due to the collision of ice crystals and graupel, or what we call hail particles. Usually in the first stage of a thundercloud, first you get the formation of very tiny ice crystals, and you also have supercooled water droplets, and these water droplets collect on these ice crystals, and it lead to what we call graupel particles, or commonly we call it hail. And when the hail is falling down in the thundercloud, because they are heavy, they collide with ice crystals, and in these collisions, electrical charges are separated. Ice crystals becomes positively charged, and the hail, which is heavy, it becomes negatively charged, and the hail comes down, and the ice crystals goes up. So the upper part of the thundercloud is positively charged, and the lower part is negatively charged. So that is the mechanism how you get electrical charges in thunderclouds. And when you increase the production of electrical charges, sooner or later there will be electrical discharges. And from a thundercloud, you can get 4 types of lightning discharges. You can get lightning discharges to ground. We call them ground flashes. Sometimes you get lightning discharges inside the cloud. Sometimes you don't see the discharge itself, you see just illuminating clouds, but the lightning flashes which strike the ground, you can see them, you see it as a bright channel. And let me now tell you a little bit of what happens during a lightning flash. And first, if you can observe what is happening with a very high-speed camera, what you will see at the very beginning is something like this. Let's start, you have the cloud base, you don't see what is happening inside, but what is happening outside you will see. The first thing that you will notice is a small electrical discharge that start coming towards the ground. I hope you can see it in the screen. So this electrical discharge, we call it a step leader because it is coming down, not in a continuous manner, but in steps. So it makes a step, and then you don't see anything, and suddenly it will make another step. In that manner, it will continue like this. So when it is coming down, actually it does not know where it is going to strike. It only knows that there is a ground somewhere down there, and it is going down in that direction, but the point of strike is not determined at this stage. And then it comes down like this, and when it is about 200 meters from ground level, what happens is, because of the high electric field that this electric discharge creates, you will get electrical discharges from objects on ground going up, try to meet this downcoming electric discharge. And so you will get electric discharge from many objects. You can get many such discharges, and they will move up to meet this downcoming electric discharge. And then the moment they meet, what happens is the electrical connection is established between the high potential cloud and the ground, and you get a very strong electric discharge with a very high current along that channel. And then that's when, that's what you see as a bright channel, and it will produce thunder. I will tell you later what is the mechanism of thunder. And sometimes it ends here, but usually there are more events in this. For example, you might get another electric discharge along the same channel, and you will get a bright flash or high current going up into the cloud, and the same continues maybe 2 or 3 times. And if you look at that lightning flash with your naked eye, what you see is only this. So this is what is happening during a lightning flash. And let me show you a video. I hope this will. Now you can, this is a high-speed video. It's 10,000 frames per second. You can see electrical discharges coming down. You can see some upward discharges going Yeah, that because you don't see anything there because the light is so bright when they meet, but you can see that still it is going on, and then the light is changing. And if you watch this illumination, you can see that it is changing because things are happening in the channel, but the illumination is so high that the camera cannot actually resolve it in time. And now the intensity is going down, and then finally you can see the lightning channel. And during the lightning flash, this thin channel is heated to a very high temperature, and the channel that you see a bright channel, and the width of that channel is not very big. It is about few centimeters thick. How do we know that it is few centimeters? Because people placed nets around very tall buildings and then let lightning pass through those nets, and then from the holes that the lightning create, they managed to find out what is the size of this lightning channel. So these are examples of those nets. So in this channel, which is about few centimeters thick, the temperature increases very rapidly to about 30,000 degrees, and then the channel expands very quickly, and that's what you hear as thunder, because that will create a shock wave which will give rise to the sound wave that you hear as thunder. And this process, this heating of the gas in the thundercloud, is very important in environmental studies. The reason is when you heat air to these high temperatures, what you do is you break the oxygen and nitrogen molecules, and when the lightning channel cools, these oxygen and nitrogen molecules, they combine, and it will give rise to nitrogen oxides. So the main process that produces nitrogen oxides in air is the lightning flash, which is important when you try to analyze the effect of man-made gases in the atmosphere. And many people, they ask me if lightning, because when you experience lightning, it's a very powerful event. They ask me, can we take the energy from lightning flashes? So let me tell you a little bit about the energy in lightning flashes. So if you take a normal lightning flash, remember that the lightning channel is about 5 kilometers long. If you take just 1 meter of the lightning channel, the energy you have in that 1 meter is enough to lift 1 ton of water to a height of 4 meters. So there is rather considerable amount of energy in a lightning flash. And the lightning channel is about 5 kilometers long, so it dissipates about 200 million joules, one lightning flash. So, but the impressive thing is all this energy is released in about 100 microseconds. So the power of a lightning flash is very, very high. And if you take the whole Earth, you have about 100 lightning flashes each second striking the Earth. So you can estimate what is the total power dissipated by lightning. It's about 20 billion watts if you take all the lightning flashes around the globe. And so if you take 1 year, lightning flashes will dissipate about 175 terawatt hours. Just to give you an idea about how much this energy is, if you take Sweden, industrial country like Sweden needs about 140 terawatt hours each year. So if you collect all the light energy of a lightning flashes, you can actually run the needs of a country like Sweden. But the problem is lightning is distributed around the globe, and you cannot bring all that energy to one single place. So if you divide it equally among all the inhabitants of the world, so we will get about 40 watts of power or energy in each square kilometer. So you can see that economical uses of energy from lightning is not very viable, but it's an impressive event. It produces lots of power, but to use energy from a lightning flash is not very economically feasible. And now let me tell you a little bit about interaction of we humans with lightning flashes. Usually, during lightning flashes, thunderstorms, sometimes children, they play outside, or there is a football game going on. They don't like to stop the game. Even when there is a thunderstorm coming, sometimes they continue to play. And consider what happens. Say that these are the players in the field, and there's a thundercloud up there, and this step leader, this electric discharge, it starts in the cloud and it starts coming towards the ground. And what happens is when this discharge is about 200 meters, 300 meters higher up, all these from the head of all these players, you will start electric discharge going towards this downcoming electrical discharge. And unknowingly, they all compete to get this lightning flash attracted towards them. So all these electrical discharges which are going up, they compete with each other. And the one who produces the longest discharge will be the one who will get the lightning strike. So there is a very big competition going on at this stage between each of these players. Of course, they don't know what is happening, but naturally this is what is going on. And one of them will receive a lightning flash, and he will be exposed to this very high current. But the others, of course, they get a discharge from their head, but they will not receive serious injuries. But the one who gets the direct strike, sometimes he can die or he will become unconscious, but only in about 80% of the 20% of the cases that the people die when they have a lightning strike. There is a reason for this. The reason why all the people, they don't die when they are exposed to a lightning strike is due to this reason. Usually, when the lightning strikes you, what happens is the current in the lightning channel starts to increase. So this lightning current, it starts flowing through your body. As the current increases, the voltage between your head and the feet, it will start increasing, and at a certain stage, there will be electrical discharge that will be formed between your head and your feet along the body. And at that stage, the lightning current will jump from inside the body to outside. So most of the lightning current, fortunately, actually travels outside your body. Otherwise, if all this current pass through your body, actually there will be an enormous explosion and the body will explode. But fortunately, because of this mechanism, that most of the lightning current is flowing outside the body. And this is a person struck by lightning. You can see the mark of this electric discharge along his body. So the lightning current jumped from inside to the outside of the body. And then, of course, this discharge can cause severe burns, and also it gives a shock wave. It can sometimes rip out the clothes you are wearing, and it will produce a shock. But in many cases, about 80% of the cases, the person can survive. And now I will try to tell you a little bit about lightning detection. Now we have equipment to detect lightning when there is a thunderstorm. We are actually able to say where the lightning is striking. And we are using two mechanisms, and all these different types of mechanisms that we use to detect lightning, it is based on the electromagnetic fields, because lightning is an enormous radio antenna. It generates radio waves. So we use these radio waves to detect lightning flashes. And for example, one method is to use the magnetic field produced by a lightning flash. When a lightning strike, it will produce magnetic fields like circles, and then they move out from the lightning strike point. So by measuring the direction of these magnetic fields at several places, you will be able to say where the lightning is. So nowadays, I mean, in many countries, you have these lightning detectors, so you can use them to detect lightning flashes. And I will show you one video where they have used these lightning detectors to detect lightning storms, and also using radar they managed to see the height of the thundercloud. So here you can see what they have produced from this. You can see that the thundercloud, it is growing and sometimes it is changing, but all these are real lightning flashes. They are detected by this lightning detection system. And so you can see that it was about 20 minutes of thunderstorm activity, and so you saw what we can do today with this lightning detection systems. There is another method to detect. Now, what happens, one problem is that we don't see inside the thundercloud. So how do we know what is happening inside the thundercloud? There is another method, what we call the time of arrival method. With this, we can actually locate, or we can time the time of arrival of the signals to different stations, and from that, actually we can locate what is going on inside the cloud. Even though you don't see anything with your naked eye, you can actually detect what is happening inside. And here is one video which shows what is happening inside a thundercloud. So you can see the enormous amount of electrical activity taking place inside the cloud, and the curve which you have up there, it is the electric field at ground level. You can see that the electric field is changing, and you can also see the time passing, and you can see the enormous amount of activity that is taking place inside the thundercloud. And thanks to these different methods, today we can actually see what is going on inside the thundercloud, and these methods were available only during the last 10 years. And we can also use satellites to detect lightning, and because they were equipped with different types of sensors to detect lightning. And this is a map of lightning detected from satellites, and you can see that one thing you can see immediately is the lightning is concentrated onto the continents. Very little lightning activity is over the sea. The reason is actually it is the continents, because of the sunlight, they becomes warmer and hotter, and that will give rise to thunderstorms. So you can actually separate out the continents when you look at the amount of lightning flashes detected by these satellites. And now, as a researcher who would like to understand lightning, we have one problem. The problem is we cannot say exactly where lightning is going to strike. Say that I have my equipment, I want to do some measurements, but the problem is I don't know where the lightning is going to strike. Should I place my camera in that direction or in this direction? It's very difficult to know. So people have invented a procedure to trigger lightning. And actually the first lightning triggering experiment, which was unsuccessful, and thanks God that it was unsuccessful, otherwise Benjamin Franklin would have been killed during this experiment. So this is actually a way to trigger a lightning flash if you just send up a kite towards a thundercloud. But the scientists today, they are using a better method. What they do is, whenever there is a thundercloud, you have rockets at ground level, and these rockets are connected. Base of the rocket is connected to a very thin wire, very long wire, and then you shoot the rocket towards the thundercloud. And when the rocket is going up, when it is about 100, 200, 300 meters, you will start electrical discharges going up from the tip of this rocket, and they reach the cloud, and then you get lightning flashes along this discharge, and then they follow the copper wire, of course, which will burn, but the vapor is enough to keep the lightning channel along this conducting path, and then since the copper wire is connected to whatever equipment you have, you can directly direct the lightning current directly to your equipment. So in this way, people are using these triggered lightning experiments to study the properties of lightning flashes. And these are examples of lightning triggered using this system. So you can see that actually lightning channel is thin, but when you have wind, what happens is this channel will move away from the original path. So that's why you see this blurred nature in these pictures. And I will like to show you one example of a triggered lightning. You can see the rocket going up, and then you can immediately see a lightning flash following along these rockets. Now you can see there the rocket went up, and then the lightning flash came down. So this is a real experiment where they shot a rocket towards the cloud, and a lightning flash was made along that channel. And actually, sometimes it's also possible that airplanes can also trigger lightning flashes. This is an airplane taking off from Tokyo airport, and in the first picture you can see the airplane, and then the second one you can see a lightning striking that airplane. And by looking at the direction of these branches, you can see that actually it is this airplane that triggered this lightning flash. So it's possible that even grounded objects or objects close to ground can also trigger lightning flashes. And finally, let me tell you a little bit about interaction of lightning with the upper atmosphere. If you go back about 15 years, if you go back, say, 15 years back, and this is what we believe. During that time, we thought that lightning, only you have thunderclouds in a special region of this called the troposphere. All the lightning, all the thundercloud activity is taking place in this layer. And we thought that all the lightning flashes, or we can say the fireworks of nature, is taking place in this particular layer between the troposphere and the earth or the ground. And we always thought that we had a much better view of these fireworks of nature than the gods who are sitting up there, because everything is covered by thunderclouds. Only we humans can see this nice activity. But about 15 years ago, we realized that we were wrong. And actually, today we know that there is enormous amount of activity going on between the troposphere and the ionosphere. All these activities triggered by lightning flashes taking place at ground level, and people call these by interesting names. They call them sprites, blue jets, elves. So there's a very colorful activity going on above the thunderclouds. So one has to say that the gods knew better than the humans where the best activity is taking place during thunderstorms. So let me show you one picture, what is happening in the ionosphere when you have a thunderstorm below. Now you will see the type of discharges taking place in the upper atmosphere. So these are the discharges taking place up there, about 70, 80 kilometers up there, but they are actually triggered by lightning activity taking place inside the thunderclouds. And also very recently, we also found out that lightning and thunderclouds can generate gamma ray flashes, these high energetic gamma rays. Thunderstorms can produce flashes of these gamma rays. And they are related always to lightning flashes, and because these gamma rays can in some way produce problems in satellites we have up there. NASA has recently launched a satellite called Firefly to study these gamma ray flashes. Actually, these gamma ray flashes are produced by lightning itself, because during a lightning flash you produce lots of electrical discharges, and these electrical discharges actually give rise to electrons, and these electrons are accelerated in the electric field of the thundercloud, and these high energetic electrons, they give rise to these gamma ray flashes. So the principle of these gamma ray flashes is produced when you have very high energetic electrons. When they collide with air molecules or atoms, then their path is diverted and it will give rise to gamma ray flashes. I will show you a little video. This is this one created just to show the gamma ray flashes, and you have these gamma rays going up, and at the same time you get a beam of electrons coming out from the thundercloud, and they travel along the magnetic fields of the earth. And within this process you actually produce not only electrons, you also produce positrons. So actually thunderclouds are capable of producing not only electrons but also positrons. That means they can produce matter and antimatter. So now I will come to the last slide just to show you where we stand today in connection with our knowledge we have about lightning flashes. And this is the picture we have today. So you can see that the lightning is something, not just something that is produced by a thundercloud, but it involves the whole Earth's atmosphere. So whenever you would like to know the effect of man-made gases in the atmosphere, then you have to study or model these events. And another thing is that now we are concerned about global warming, and scientists, they have calculated that if you increase the global temperature by about 1 degree, the lightning frequency will increase by about 10%. So if you measure the activity, lightning activity around the globe, actually you can use it as a thermometer to study the change in the global temperature. So with this, I would like to end my speech. And if you have any questions, of course, you are very welcome to talk to me later after this presentation. Thank you very much.